So one of the main things, so we'll learn some properties of the sets, but we want to prove them, not just to give you those properties. So we want to see how to prove that two sets are equal. And here's the standard way. It's called the member test. So we prove equality of two sets using the member test. Actually, I just showed here how to prove that one set is subset of another one. So how do you prove that A is a subset of B? Here is the method of proof. You choose an arbitrary element from A without any special assumptions. And then you prove that that element also belongs to what? B. So that's it. So pick an arbitrary element, don't assume anything special about it, and then show that it belongs to B, nothing else. So let's see how it works in a specific case. By the way, you might be able to recognize that somewhere in the middle we'll switch from sets into logic, into chapter 1. So you can notice that I will just repeat this proof from the note. So here's an example. Prove that A is subset of A union B intersection A. Generally, we'll develop in this chapter two ways to prove things. One comes later. When we develop a library of knowledge about sets, then we can call those properties, but we don't have anything yet, so I cannot call that method. So here's what we'll do very often. And that's unbelievable how often this works in mathematics or anywhere in proving. So here's propositional logic. Here are sets. So if you want to show, no, yes, river again, yeah. So here's the river, and then here it is. Among the propositions, you do have a bridge. What is the bridge? A bridge are tautologies. Between the sets, you don't have a bridge. So here is one set, and here is the other set, and you want to show that they are equal. What are you going to do? So what do you need? But this is propositional land, and this is sets land. So what do you need to do? To translate for sets to propositions, use tautology to cross the river, and then translate back from proposition to sets. Why am I drawing this? I do it in all of my courses, because that's really what's happening. And you can see step 1, step 2, step 3, and they change from problem to problem, but methodology is always the same. So let's see. So we said the following. So here's, so we said X belongs to A. We pick an arbitrary element. X from A. At the end, what do I need to get? That it belongs to this set. Do you agree? All right. Now we'll say the following. X belongs to A implies X belongs to A or X belongs to B. Do you agree with what I wrote? First, is it correct? Second, why do I care about this? Why did I decide to write this? Is this correct?
The other thing I don't get is why does it imply that it could be belongs to B?
Why does it imply? Here is the reason. So I'm switching to propositional land, and here's what I'm saying. Is it true that P implies P or Q? Is this always valid, yes or no?
Yeah.
Why? Make a table or what? If P is true, then disjunction is true. So is it correct logically, yes or no? Why do I need it? Because of that union. So I'll say the following. Since I already assumed that X belongs to A, and then, so this is true because of this. Now I have the following. I have P, this is one line number 2. In line number 3, I said the following. I have P, and I have P implies Q. What can I conclude by modus ponens? Q. So that means I can conclude X belongs to A or X belongs to B. So that, and one of the things that you need to keep in mind is when I write sets, I write equal. When I write statements, I write equivalent for statements. So here it is. X belongs to A. Is that a set or a statement? Statement. So if it's statements, I do and, or, and so on. If they are sets, I do unions and intersection. So once again, why did I do it? Because of the union. Why is it correct? Because of this tautology. And then between lines 1 and 2, I got X belongs to A or X belongs to B. But then what? If X belongs to A or X belongs to B, what can I conclude? One more modus ponens there, but I'll rush that a little bit. Can I conclude that X belongs to A union B, yes or no? If it belongs to one of them, does it belong to union? Is this definition of the union? So this is by definition of union. So you always justify your line of union. Line number 5. X belongs to A, an individual. So can I say that I have both X belongs to A and X belongs to A union B, yes or no? Do I have X belongs to A from the beginning, yes or no? Yes. Do I have X belongs to A union B? So if I have them both individual, I have their conjunction. By the way, that's the method of inferences. If P and Q, then I have P and Q. So what then? So now I have what? X belongs to A and X belongs to A union B. If you belong to both sets, what do you belong to there? There what? If you belong to both sets, you belong to their intersection. So X belongs to A union B, intersection A. And that's your right side, so I proved that it's really a subset. This is how you prove something is a subset. So every line has to be justified basically using the appropriate propositional formula. Particularly in the beginning, I want you really to justify every line and to be aware of all this so that you develop that habit, and then later on we'll do a little more sketchy proofs. By the way, I did something else for a moment, and that is when I assembled them, you see that this statement comes second, and here I put it first on the intersection. So what should I do? Shall I flip them? Yes, that's commutativity of the conjunction. So, I didn't really split here on each of them. But this is how you prove that two sets are subsets of one another. And if they are equal, you need to show that if it belongs to left, belongs to right, and back. So that's how we prove that statements are, that set is subset of the other one. And then, we'll just practice this, and let me just summarize what happens here. Using this, we can prove the following set of identities. Can we comment on the set of identities? So here's the whole list. What can you notice between the left column and right column? I'm not asking you to memorize it. You use it all the time in mathematics. So this is just to have them listed on one spot. Can you see how our left and right column are related? Opposite in which sense?
The union versus the...
Union and intersection are switched places. Yeah, so on the left you have union, on the right you have intersection. So what is the first one saying? If you take union of a set with itself, you get A. Is that common sense? Do you want, if someone wants me to write proof, I'll write an easy proof like this one. So I would say?
P or P.
Exactly. It is actually P or P will be propositional content. In the middle, you will see that one. So this is just actually other phase of the propositional tautologies. Then what about second one? What is that telling you? That union is commutative, okay. What about third one? Associative, very good. What about fourth one? Fourth one is new. No, fourth one is something that you don't see in regular algebra. This is called absorption law. If you take A union A intersection B, you will just get A. That's not this. This is much more subtle, and we'll prove that one after the break. That's an interesting one. But let me see the list so that we are all aware of that list. What about this one? Distributive law. But distributive law works both ways, not like for plus and times. So when union is outside and then connects to both B and C, or when intersection is outside connecting, then what? A union empty set is what? A, you don't get any new elements. And then A union A complement is what? The whole universal set. By the way, these are famous axioms that they look like, properties of numbers, like adding 0, or here adding the opposite or something like that. So, and what's this? Does this look familiar?
De Morgan.
It is De Morgan for sets, yes or no? If you take complement of a union, what do you get? Union becomes intersection, and then sets get their own complement. So that's really De Morgan's law for sets. How do we prove it? Once again, as I said, I'm not taking these for granted. I just wanted you to be aware of this list. And then we'll prove a couple of lines. And then what is the good thing? After we prove this, that will give us alternative way to give proofs about new statements. You can either go to logic and cross the river all the time, or call this table and then combine facts from the table to make shorter and quicker proofs. So that's what we'll do in the second hour. But let's take a break now. We continue at 2:35.